Welcome everyone to today's science seminar. It's my great pleasure to introduce today's speaker, Professor Dipankar Bhattacharya. Professor Bhattacharya is the Sunanda and Santimay Basu Chair Professor at Ashoka University. He's also the head of the physics department at Ashoka University. Professor Bhattacharya was previously associated with the Inter-University Center for Astronomy and Astrophysics, or IUCAA at Pune, and the Raman Research Institute, Bangalore. He obtained his BSc and MSc from Jadavpur University, Kolkata, and his PhD from Indian Institute of Science, Bengaluru, in the Joint Astronomy program. And later on, he did postdocs from University of Amsterdam and University of California, Santa Barbara. And his research interests include high energy phenomena in the universe, and with specific emphasis on space-based detectors. So over to you, Professor Bhattacharya. We are very delighted to have you here. Thank you.
Thank you very much, and many thanks to Indian Association for General Relativity and Gravitation for making this possible. Today, given the theme of the IAJRG lecture, I decided to cover a topic which relates to general relativity and gravitation, and in particular strong gravity signatures around compact objects. So let me begin with introducing what are compact objects. So compact objects, compact stars, are remnants of stellar evolution at the end of the lifetime of a star. So star during its normal lifetime, it spends first burning nuclear fuel at the center, and at some point the nuclear fuel runs out, so the core begins to condense with further nuclear fuel burning around it, which keeps adding material to the core. And eventually, when all the burning is finished, the outer part of the star gets expelled, either gently, like in a planetary nebula, or violently, as in a supernova, and you are left with the central part of the star in a very compact form. It could be either a white dwarf, which are Earth-sized objects, or neutron star, which are city-sized objects, or a black hole, which is the most condensed form of material that exists. So these are normally referred to as the compact stellar remnants. And today, for this specific lecture, I will concentrate primarily on neutron stars and black holes because they are extremely relativistic objects. So I will introduce in a moment what I mean by that. Neutron stars have masses round about 1.5 times the mass of the Sun. The lightest neutron stars known are about 1.2, 1.25 times the mass of the Sun. The heaviest known is around 2.2 times the mass of the Sun. The radii are of the order of 10 kilometers. But if you take this much mass and concentrate onto this small volume, you will note that the average density of these objects are like the density inside an atomic nucleus. And the surface gravity is more than 10 to the power of 12 times the surface gravity on Earth. So the escape speed from such strong gravity is nearly 70% of the speed of light. So you can still escape if you are standing on the neutron star, you can still escape. But you will need rockets which are far larger than whatever NASA or SpaceX or ISRO has built. So the gravitational binding energy is about 20% of the rest energy of these objects. And it is these parameters which classify it as an extreme relativistic object. Neutron stars also spin, and some of them spin very fast, about spinning around its axis of the order of a millisecond. Some spin a bit slower, a few seconds, but imagine the Earth rotates on its axis once every 24 hours. And now you have an object which is 1.5 times the mass of the Sun, condensed within 10 kilometers, rotating on its axis 1,000 times a second. So these are highly exotic objects for that reason, and therefore create the kind of phenomena near the surface which are not seen in any other setting. They also have very strong magnetic fields, on an average of about teragauss, but going all the way from gigagauss to about a petagauss. So given this very strongly relativistic nature of these objects, you need to use general relativity to describe anything that goes on in this object, including its internal structure. However, we still do not have a full understanding of how a neutron star is, what is entirely contained within the star, and that is because there is still some uncertainty in its equation of state, which means how does pressure behave as a function of density. So if you take a piece of material, squeeze it to some extent, with what force is it springing back? And that decides how we pack material in a star by the force of gravity. And we don't know equation of state of neutron stars very well, because we have now squeezed fundamental particles so close to each other that there is no terrestrial laboratory measurement which has probed that regime. So we can only take observations that we have and extrapolate it to that regime. And as you can know, that all extrapolations are ambiguous. So therefore, we do not have an exact idea of how fundamental physics like strong interaction works in such small scales. So that is a problem for neutron stars. But you can turn the problem around and then say that, so if we can make a measurement of the structure of the neutron star, even simple things like mass and radius, it can tell us something about fundamental physics like strong interaction. And that is one of the active research areas in neutron star physics. Black holes, on the other hand, matter has gone beyond all recognition. We expect them to have collapsed into a singularity of some kind or some quantum form, whatever it might be. But it is surrounded by a horizon from within which no information can escape. So therefore, we cannot know in what form the matter is inside. We would never know. But what we can see is only phenomena that occur outside the horizon. So these are objects which are even more compact than neutron stars. So if you take the mass of a neutron star, let's say 1.5 times the mass of the Sun, then its horizon radius would be about 4.5 kilometers, which is even less than this 10 kilometers we are talking about for a neutron star. But it also tells you that neutron stars are indeed very close to becoming a black hole themselves. A black hole could have just 3 possible attributes. It's a very simple object, unlike neutron star, which can have magnetic field, which can have deformation and so on. A black hole can have only 3 attributes, that is its mass, its spin, and an electric charge. But in nature, we are hardly likely to encounter a black hole which is electrically charged, because it can always attract opposite charges from elsewhere and neutralize itself. So astronomical black holes, we tend to describe only by two parameters, which is mass and spin. Once you know the mass and the spin, you know everything about that particular black hole. So now black holes, of course, cannot be seen by themselves. It is not self-luminous, no radiation can escape from it. So how can we ever observe a black hole? So you don't observe a black hole itself, but you observe phenomena occurring around the black hole, such as matter from elsewhere coming and falling into the black hole. And matter falling into the black hole may release up to about 50% of its rest energy. So up to 50% of mc squared can be released while falling into the black hole, depending on how you make the matter fall. The observed masses of black holes lie in the range about 5 solar masses, the lightest one we have measured, and billions of solar mass at the centers of galaxies. So black holes can be of any mass, unlike a neutron star or a white dwarf where there are specific limits. The black holes can be of any mass. You can even have very light black holes if you find a means to produce them. And it can have any large mass that you want. The biggest ones we see are in centers of galaxies. We call them supermassive black holes. At the center of our own galaxy, the Milky Way, there is a black hole which is measured to be of 4 million solar masses. And there are other cases in other galaxies where you have seen black holes which are of the order of billion solar masses. So these supermassive black holes are not formed in an event like the supernova event at the end of stellar evolution, but they grow over cosmological time scale. So there are two types of black holes that we'll be talking about. One is this stellar mass black holes, which are produced in these supernova events, and the others which grow over cosmological time scale and are found at the centers of galaxies. How do we study these objects? We of course study them in their electromagnetic radiation, but to study compact objects and the phenomena I'm talking about, you cannot confine yourself only to a small band of wavelengths, but you really need to go very wide, all the way from radio to gamma rays. And we also find signatures of compact objects in gravitational ways. So all kinds of observatories are involved. In many electromagnetic wave bands, our atmosphere is opaque. Radiation coming from outside does not reach the ground. So clearly, we cannot build ground-based observatories at all these wavelengths and expect to observe them. So the two windows in which we do have ground-based electromagnetic observatories are radio and optical, where radiation does reach the ground. But in all these other bands, in the infrared, ultraviolet, X-rays, gamma rays, we have to put detectors well above the atmosphere. And these days, we just build satellites, put detectors on them, and launch them in a rocket, and they stay up in the orbit for a long while and allows us a platform to observe. Through my lecture, I will allude to several observations that we have gathered from an observatory called AstroSat, which is something that India built and launched 10 years ago. In fact, on 28th of September will be the 10th anniversary of the launch of AstroSat. And I will use some few glimpses of results from that in this lecture as well. So neutron stars are observable in primarily radio wavelengths through this phenomenon called pulses. So they are strongly magnetic objects, rotate very fast, so they produce beams of radiation. And every time this beam of radiation crosses our line of sight, you will see a pulse. So every rotation period, you see a pulse. So this is a very accurate clock because you are measuring the rotation period of this object. And the property of these being very accurate clocks is something that will play a role in some of the observations that I'm going to talk about later. So keep that in mind. So this is largely seen at radio wavelengths, but there are many pulsars which are also seen in X-rays and gamma rays. The larger numbers are in radio. And in X-rays, we can also see neutron stars in another form, where here is a neutron star which can pull matter off another normal star which may be sitting around it, but the gravity of the neutron star is strong, and if the star is close enough, matter can be pulled off its surface and fall onto the neutron star. Except it will not fall radially like in a straight line, because there is an orbit, the matter carries some angular momentum, so it will go around and by friction usually gradually lose angular momentum and eventually fall into the neutron star, fall onto the neutron star. So this is a disk-like structure which we call accretion disk, and the friction of matter as it comes closer and closer to the neutron star releases more and more energy. It begins to get hotter as the matter approaches the center. So this disk structure which is cooler on the outside and hotter on the inside, and the inside, when you have a compact object like a neutron star or a black hole, gets so hot that it glows brightly in X-rays. And in fact, these are some of the most luminous individual X-ray sources around. So, and these are called accretion-powered X-ray binary systems. Some of these neutron stars can also display their rotation in the same way as that, so you can call them X-ray pulsars. Some of them, the rotation is not so easily apparent, but you may be able to find their signature in other timing behavior of these objects. Black holes, on the other hand, will not have any surface phenomena that you can see, but the presence of a black hole will be revealed by the behavior of matter that is swirling around it and falling into it. So if a black hole has a companion, matter will come like as I described in the case of a neutron star. The matter will come and then it will swirl around and then it will fall into the black hole at the center. It is often accompanied by some matter being ejected in the form of a jet, and there are some strong winds which could be expelled at some time. Sometimes the jet may be present, sometimes the wind may be present, sometimes a corona may be present. And this disk usually extends to an inner radius, which we'll call the inner edge of the accretion disk, let's call it. And some of the phenomena that I will describe are dependent on how far in the inner edge of the accretion disk is. And as you will see that they are related to some fundamental properties of these black holes. Another way the presence of a black hole can be revealed is not by any direct radiation, but just by its gravitational influence on the dynamics of stars around them. And this is a 25-year time-lapse picture of positions of stars around the center of our galaxy. And over time, as you can see, the stars describe individual orbits, and from these orbits you can easily tell what is the mass contained within around which these stars are orbiting, and it is from that this estimate of 4 million solar masses comes about. Now, if you take an orbit like this, in this one picture, it looks like a close elliptical orbit that is going around. But if you look at it in detail, you would notice that this orbit is not actually closed. Every orbit is displaced with respect to the previous orbit a little bit, like that. And this this displacement in this case is about 12 arc minutes per orbit. And this is a characteristic of relativistic effect. Some of you may know that one of the first relativistic effects to be measured was the precession of the perihelion of Mercury in the solar system. That's excess precession of 43 arc seconds per century. And it is basically the same effect, which shows up here. And because around the black hole the gravitational field is very strong, you get a much more amplified effect, which is 12 arc minutes per orbit. One orbit in this case is 16 years. So it's about a little less than an arc minute per year compared to the precession of Mercury, which is 43 arc seconds, which is fraction of an arc minute in 100 years, right? So this is one of signature of a strong gravity effect that I'm talking about. Now, as this star passes by from the nearest point to the black hole, which is called the periastron, you can keep measuring spectral lines from the star and then keep track of its radial velocity. And as it passes nearby, you see that you get some drop in radial velocity than what you expect. And this happens because there is a time dilation of the signal coming from there to here. So the frequency gets excess redshift because of the gravitational redshift, because photons have to climb this gravitational potential. So there are two effects which combine the same way, so we can only find the sum of it. One is the gravitational redshift, and other is when something is moving across your line of sight, there is a time dilation effect for that too. That's called transverse Doppler effect. Both of these have similar effect and add to the net effect, and these are both explicitly relativistic effects. So, and they're seen in strong gravity, and you can see this excess over what would be expected if this shift was not there. And this is a clear measurement of this gravitational redshift and transverse Doppler shift. So this is another strong gravity effect which you can see from this system. So we're talking about orbits near black holes or compact objects. So it's good to pay a little attention to slight details about these orbits. What I've plotted here are some kind of effective potential curves. The red line is the effective potential in Newtonian gravity. Okay. So, and here this line of 1 separates bound orbits from unbound orbits. So let's pay attention to the bound orbits. So all energy values which are below this in a Newtonian gravity will intersect this red line at 2 points. And those are the two extremities of the orbit, one could be periastron and apastron. And you will always have, as long as the energy is negative, you will always have 2 points where it will intersect. So it will have a bound orbit. And it turns out in Newtonian gravity, this oscillation period between the two extremes in this radial distance, that period is exactly equal to the time it takes for the orbit to go around exactly one rotation. So that means the frequency of radial oscillation and frequency of angular oscillation is equal, which gives you closed orbits. Now, what I've drawn in blue is what happens when you take general relativity into account for a non-rotating black hole, let us say. So called a Schwarzschild geometry. So here, just because you have a negative energy doesn't mean that you will have a bound orbit. Up to a certain angular momentum, you will still have bound orbits, right? But if the angular momentum goes below this, then just having a negative energy does not ensure that you will have a bound orbit. So, if, for example, this curve, if the energy happens to be between here and here, you actually don't have a bound orbit because you don't get two crossings. So, let's name this something. This is a critical orbit. That's called the marginally bound orbit. And in Schwarzschild geometry, that has a radius of twice the horizon radius. This horizontal scale is radius in units of horizon radius. This is where the horizon is, and this is at twice the horizon radius. Now, all these curves have a minimum. So, if your energy happens to be such that it crosses the curve at this minimum, then both the left and the right crossing points of this line come together and is at one point. So, that means the radius of the orbit is not changing, it's exactly fixed. But of course, the angular thing is going around. So, the fixed radius but going around is a circular orbit. So, at the minimum of these curves are circular orbits. Now, all of these curves also have a minimum. So, you can all of these curves can have circular orbits at all these angular momenta. But once you go below this angular momentum, there is no minimum in this curve. So, you cannot have a circular orbit. So, and as you go from here to there, the circular orbits come nearer and nearer to the horizon. So, there is an innermost value of the circular orbit which belongs to this curve, which is at 3 times the horizon radius. And this is called innermost stable circular orbit, or we refer to it as ISCO, YSCO. All of these are important for further discussion, so I am going to introduce this. So, we have learned that there is an ISCO, there is a marginally bound orbit, and next to remember is that since these curves have a different shape compared to the red curve, the radial oscillation frequency is not going to be the same as the angular oscillation frequency. So, therefore, the orbit is not going to close. By the time it comes around, the radius is shifted by a different amount. So, orbit is going to precess around, and that is exactly the precession that you saw in the previous slide, right? So, it's called the precession of periastron. Angular momentum of the particle coming in. The black hole itself is not spinning. Yeah. So, that's about particles. What does it do to radiation? So, radiations are like massless particles, photons. So, if you look at the orbits of photons in this Schwarzschild gravity, you have light, which we are used to light traveling in a straight line. But gravitational field does bend light, and when you have black hole with such a strong gravity, it bends light strongly, and these are calculated bent light trajectories going at different distances from the black hole. You can see some of them will bend, some of them bend quite a bit, go in a completely different directions from which it came. Some will just fall in, no escape. And there is a specific trajectory which can get trapped over here. Okay? And that light trapping distance is at 3 times the or 1.5 times the horizon size, 3 times gm by c square. So, we saw one critical radius at 3 times the horizon radius in a most stable circular orbit, one critical radius at 2 times, which is the marginally bound orbit, and this is at 1.5 times the horizon radius. So this is what can happen. You have light bending, you have photon trapping, and once you have these bent light trajectories and light moving through it experiences strong gravity regions where, because of gravity, clocks slow down. So you get delays, both because light has taken a longer path and also because it has traversed regions where clocks slow down. So those are propagation delays, and the wavelength of light is going to change. Because once you move from a strong gravity region to a region further away, your frequency you see at infinity is this factor where this is the gravitational potential at the place of origin, right? So the frequency at infinity is reduced with respect to the frequency at which the light was emitted. So that's called gravitational redshift. So all of these effects are going to affect the propagation of light. Some of you may have seen this picture. It's a famous image of a black hole, which was published by the Event Horizon Telescope. And basically what you're seeing here is radiation from material which is surrounding the black hole, and they're emitting, and the light from that coming around the black hole and then coming to us, and that is why it looks like this with a shadow inside. So these are all bent light trajectories which produce images like this. And this is a billion solar mass black hole at the center of the galaxy called M87. So that's Schwarzschild picture. Now we make the black hole rotate. The primary result of that is all these critical orbits, the critical surfaces that we're talking about, they shrink if the rotation is prograde, and they will expand if the rotation is retrograde. So let's talk about prograde. Then at zero black hole angular momentum, you start with, let us say, the innermost stable circular orbit, which is 6 gm by c squared, which is 3 times the horizon radius. So this is the horizon radius. Okay. As the angular momentum increases, this radius is going to come closer and closer to the center. And so is true for all of these. This is the marginally bound orbit, this is the photon trapping orbit, and this is the horizon itself. This is the polar coordinate of the horizon. And J being the angular momentum of the black hole, M being the mass of the black hole, this quantity can only go from 0 to 1. You cannot have an angular momentum larger than this, and this is called the critical angular momentum or maximally rotating black hole. And this is Kerr geometry, and these are called maximal Kerr black holes. So now let's get a bit closer to what we can observe. We looked at accretion disk, and accretion disk contains matter. You can consider those as particles going around the central black hole. They'll come closer and closer, and the disk gets hotter and hotter. So this is the temperature profile of a disk coming from outside to wherever the inner radius is. So as I already mentioned, the inner part is hotter, and the scaling temperature here actually becomes larger if the inner radius is smaller for the same mass. So this hot disk is going to produce a spectrum which you can observe, we can measure. And the spectrum will be related to the temperature distribution as well as relativistic effects like Doppler shift, gravitational shift, etc. So if you observe the thermal spectrum from the disk, you should be able to decipher this temperature distribution along with the relativistic effects, and it should be able to tell us what is the inner radius of the disk. And the inner radius of the disk depends on the mass and the spin, because The innermost stable circular orbit, as we saw, depends on the mass and depends on the spin. So if we are able to measure this, we should be able to actually find the mass and spin of the black hole. And this is one of the relativistic effects that we measure. These are continuum spectra built from simulations for different parameters. So let us say different angular momenta for a black hole of the same mass, and you can see that the expected spectral shape and the extent differs. So what about actual observation? So you can now take an actual observation, find the spectrum, and then use this method to find the mass and the spin. And here is one such object for which some of our own group members have worked, used some astrosat data, some data from Chandra X-ray Observatory, and together we have a constraint. This is the combined constraint in the middle one on the black hole spin parameter, which in this case is very close to 1, 0.92. So this gives you the ability to measure black hole mass and spin by use of these relativistic signatures, right? So relativistic signatures are not only observed, but it allows us to deduce properties of the black holes. What if you had a spectral line in this swirling mass which is arriving and being accreted at the center? How will that profile of the spectral line look? So you have to take account of the rotational Doppler shift. Some part of the material is going away, some part of it is coming towards you. So there will be blue shift and there will be red shift. And this whole thing is situated in a region of strong gravity. So there is a total gravitational redshift. So you have this widened profile because of rotation and shifted to longer wavelengths or lower frequencies because of gravitational redshift. So when you put all of that together, so these are predicted line profiles for different inner radii in units of Schwarzschild horizon radius. In a radius of 100 horizon radii, you see spectral line being broadened like this. So these different figures are for different inclination angles with respect to line of sight. So as you see from top where you are not seeing the rotation, you will see a profile which is not blue shifted or red shifted, but only gravitationally red shifted. So you see a single profile. You come to any other angle, you see the blue shift red shift, so you get wings, and these wings are shifted by gravitational redshift. So these are different angles. R star of 100 is far away, so the gravitational redshift effect is small. Now as you keep bringing it closer and closer, this is 11, this is 5.5, this is 2, and you can see the lines begin to take a characteristic shape with a sharp blue edge and the red edge blurred into practically into oblivion, right? So these are called the blurred profiles. And how far and to what extent this blurring will occur and what this functional shape is will depend not only on the mass of the black hole and how far the material is, but also on the spin, because spin decides how close to the center of the black hole that the material can move. So this is an actual observation from a NASA satellite called NuSTAR. So all these points are from there, and this blue line shows what would have been the profile of a spectral line coming from iron, which has a transition at 6.4 kilo electron volts, and the yellow shows what is actually observed. And this blurred profile, as you call it, and the fit to it can help us measure the mass and spin of black holes. But it is not restricted to black holes alone. We can apply similar technique to neutron stars as well. And these are some observations of this relativistic line profile from neutron stars. And you can see the same blurring effect because of the strong gravity near neutron stars. See, if the strong gravity wasn't there, you would not see this one-sided blurring. Now I go on to another effect which we observe from accreting black hole binaries, and that is radiation being produced somewhere in the binary system, getting reflected off some another part of the part of the accreting system, and then coming to us. So we get some radiation which is direct, some radiation which is reflected. And since the reflected path is longer, you would expect a delay in the arrival of the reflected radiation. And this delay can actually give you a measure of the distance between where the radiation is being produced and where the reflection is occurring. And this is an effect often seen in accreting black hole and neutron star binaries. And here is an example of a very bright black hole binary transient which erupted in 2018. It's called Maxi J1820 plus 070. This will make its appearance once more in my slides. So you can hold the name of this source in your mind. So what this is showing here is this delay between. So this is delay as a function of frequency of fluctuation of intensity. And these delays are between slightly higher energy photons to slightly lower energy photons. And the delays being negative tells you that the lower energy photons are arriving later. And those are exactly the signatures of high energy photons being created through a hot corona and then reflecting off the disk, which is a little cooler, and then losing energy and coming to us. So the delay is between the direct and the reflected emission. And as a function of time, you see this delay evolving both in frequency and amount of lag, and that can be directly mapped to what is happening to this radiating corona. It's starting from a long elongated shape and then coming closer to the central black hole as time progresses. But what is important is that the amount of radiation that you receive directly versus the amount of radiation that you receive reflected, that ratio also changes. And that ratio cannot be simply computed by looking at a straight geometric effect, drawing straight lines and looking at how much area is exposed. And that is because as the radiator effectively comes closer to the black hole, the light bending becomes much more strong, and all rays are bent very strongly and illuminates only the small inner part of the disk and not reflections like that. Though reflections like that are precluded. And that decides also the character of this reflected radiation and the delays. So this gives us again some estimate not only of the size of the corona but also the mass of the black hole. Now I have shown you a picture of the swirling matter near the black hole, right? In general, the orbital plane of the incoming matter need not be exactly aligned with the rotational equator of the black hole. If the black hole spin is slightly tilted with respect to the disk, then an important relativistic effect is that black hole tries to drag the space-time near it along with its rotation. So any material that is coming close to it will be tilted and dragged close to its equatorial plane. So if you allow material to approach the black hole in a direction which is slightly different from its equatorial plane, then the inner part of the disk is going to get detached and is going to start precessing. Now let's see if this, this video does work. And so here's a simulation. This is one of the most expensive simulations that I have heard of. It used more than 6,000 GPU cards for nearly 1.5 years. So these are not simulations that you and I can easily repeat, but it does show very interesting properties of the inner part of the black hole, of the accretion disk. You will notice that the inner part of the accretion disk detaches and it starts precessing in its own time scale. And that time scale is related to the inner edge of the accretion disk. So if you were to see radiation from this system now, you will see a signature of this precession frequency. And it will look like a quasi-periodic signature in the intensity fluctuation that you see from this object. And this is an observation of the intensity fluctuation power spectrum from one such black hole, GROJ 1655-40, and you see several bumps here, 2 here, and then there's one more at higher frequency, which is beyond the scale here. So you get 3 frequencies here simultaneously present, and as time passes you will see all these 3 frequencies change, and there is some relationship in this change. Now you can identify these frequencies with different general relativistic frequencies that you can identify for these orbits. Typically for an orbit you have a rotational frequency, a radial frequency. We talked about both these before. And then there is also vertical oscillation frequency. So once you have these 3 frequencies, you can construct, one is a precession frequency, that's the difference between the radial frequency and the rotation frequency, and is a nodal precession frequency, which is the difference between the vertical frequency and the rotational frequency. So the observed light modulation is going to take place at the orbital frequency, the periastron precession frequency, and the nodal precession frequency. And all of these quantities are functions of the angular momentum of the black hole, the mass of the black hole, and the radius at which this effect is occurring. Now, there are predicted relationships from general relativity. Now, if you take these 3 frequencies and then plot them, and then look at the predicted relationship, and those are these dashed slanted lines here, and you can see the fit very well. And therefore, from these measurements, you can derive these quantities, which is the spin rate of the black hole, the mass of the black hole, and the radius at which this effect is occurring. And here you get a measurement of the mass, which is about 5.31 times the mass of the sun, and the angular momentum in units of normalized units of 0.29. You can go from 0 to 1, and this is somewhere in the middle, so 0.3. Here is something that we did. This is led by Yash Bhargava, one of my former PhD students. Same object, Maxi J 1820, that we talked about, the coronal movement. When you take the power spectrum, we actually see 3 frequencies in it. And we followed it for a while to see how these frequencies behave. And we saw that they follow exactly the kind of line that I showed in the previous diagram. And then we can turn it around. We can use this to constrain the mass and the spin of the black hole. So here is the best fit value is 10.5 solar mass and spin parameter over 0.77. Okay, so these are explicit measurements of relativistic parameters near black holes, which give us a window to the values or the properties of the black holes themselves. Now, this technique is not limited to black holes. This is a neutron star X-ray binary where there is an accretion disk which is around a neutron star. Now, neutron star, and here is a power spectrum of it, and you can see clearly multiple peaks here. This is one frequency. This is actually just the harmonic of that frequency. This is not an independent oscillation. So here is a one independent oscillation. Then there is one independent oscillation here, and there is third independent oscillation here. There is a fourth one here, which is actually this one beating with the spin of the neutron star and then producing another peak. So that is not an independent oscillation. So there are 3 identified independent oscillations, just like in the black hole case. So this troika can then be used to plot a similar diagram, and these lines are the expected relationship from the relativistic precession model, and you can see that they fit reasonably well. So in case of neutron stars, once you use this, this produces a constraint on the moment of inertia of the neutron star and the mass, right? So the why moment of inertia of the neutron star? Because the spin of this neutron star we already know. Okay, it produces a constraint on the angular momentum and mass, but the spin angular velocity we already know. So it's the moment of inertia and the mass. This is led by Keval Anand from IIT Kanpur, and part of the contribution is from one of our PhD students at Ashoka as well. So, given that constraint on moment of inertia and mass, and here is where the measurement lies, I can now compare this with the predictions from different equations of state, which can still not be distinguished theoretically, right? So we can predict moment of inertia versus mass for various different equations of state and then see which are reasonably close to this measurement. And that picks out a bunch of equations of state which are still allowed by this measurement and several which are not. So you can rule out some models of the strong interaction between particles, right? So that's a very fundamental physics kind of measurement. Now, this particular observation is from a mission which was specifically built to produce constraints on neutron star equation of state. The mission is called NISA, which expands as Neutron Star Internal Composition Explorer. Okay, so nice. That's NISA. It's a detector with a mount which is located on the space station, and it uses the space station and points to whichever direction you want, and it makes this measurement. And one of its tasks was to take a few pulsars and then measure their pulse profile to great detail. And here is one such measurement. Over several years, this is a very detailed measurement of the pulse profile, and it is measured not just at one wavelength, but at a whole bunch of frequencies. And this heat map is showing you the pulse profile as a function of frequency. Each of this, you take a horizontal cut, you will see a profile like this. It's a 5.75 millisecond period. It's rotating on its axis once every 5.75 milliseconds. And once you now try to interpret this, you will note that any point on the surface of the star which is emitting. Radiation from that gets modified when it comes to the observer due to several relativistic effects. One is light bending, something that I have already mentioned. So here's a diagram. You take several points on the surface of the neutron star which will all emit in the direction of an external observer at the same time. So ideally, if you have one line of sight and if you didn't have light bending, there will all be parallel rays and some part of this star will be seen. But because of the light bending, you can see even some of the backside is seen at the same time. So you have to take this effect into account. You have to take Doppler boosting into account because it's rotating once every 5.75 milliseconds. That means the surface is moving at a great speed. Something is coming towards you at high speed, its radiation is boosted. When it's going away, its radiation is diminished. And of course, gravitational redshift. So put all of this together, and then you can take this measurement and try to interpret how the radiation must be located on the surface of the star. And this is one of the latest reconstructions of based on this measurement of the hot spots on the surface. This is hotter than this region. The color code here is the temperature. Now, what has gone into this is a measurement of all these effects. What do these depend on? They depend on the mass and the radius of the star. So once you have this measurement, you have a constraint on the mass and the radius of the star, which is an important constraint in trying to find the neutron star equation of state. So if you have, so this is the star I was talking about just now, and there are several other stars where the mass is not so tightly constrained as this one, but these are all nicer measurements. Together they form a kind of allowed region of mass radius values of these neutron stars. Now, mass versus radius are traditional predictions from different equations of state. So for different equations of state, you have these different predictions of mass radius relations, which are shown in black lines. Now, if you now pick out a region from these measurements, which are coming from direct relativistic parameters, you see that some equations of state are allowed, some are not allowed, right? So this goes in the direction of getting further information on the strong interaction at short distances. What I have not yet talked about is using pulsars as tools to measure gravity around them. And for this, pulsar timing is a very important tool. So you have a pulsar which is Doppler shifts towards the observer, Doppler shifts away from the observer as it comes close or goes away. So the pulses will be crowded together if it is coming towards you. They will be spaced further apart if it goes away from you. So the same technique that we apply for spectral lines can be applied to pulse period. And this can be done with great accuracy. And things like orbital motion of pulsars can be probed with excellent detail using this kind of measurement. For example, the two neutron star binary 1913+16, where you can measure, you can see one such pulse. The other one is not pointed towards us, so you do not see pulses from this. But even from this one object, you can measure its motion so accurately that you can find a whole lot of relativistic parameters, that is post-Keplerian parameters. You can find the precession of the periastron. You can find the Einstein delay, which is due to gravitational redshift and transverse Doppler shift. You can find Shapiro delays. The Shapiro delay is when the signal from one pulsar is coming towards you through the gravitational field of the other pulsar, very close. So you have you have sampled the gravitational field of the other object. Then the angular momentum of this pulsar can precess, which is a geodetic precession. You can find the change in the orbital period over time. You can find the change in eccentricity over time. All of these can be found from these measurements. So there are a whole host of measurements which are far more than necessary to actually fully characterize the orbit. And these are all predicted from relativity or any theory of gravity. So you can then turn it around and start testing the theory of gravity itself, and then see if all these measurements are consistent with what is predicted from a theory of gravity. And this is one such example. This is from another object. It's a double pulsar where both the pulsars could be observed by us. And so this is usually displayed in this mass diagram. So there are two neutron stars. You have mass of one on the horizontal axis, mass of the other one at the vertical axis, and using any of those measured parameters, you predict what is the curve on which this mass correlation lies. Yeah. So let's take one measurement. Let's say Einstein delay. Given the measured Einstein delay, your masses of these two objects must lie on this line. Let's say the precession omega dot. Given them, the masses of the two objects must lie on this line. So clearly, where these two intersect must be the values of the two masses. And now we have several other measured parameters. If the predicted values from these different parameters are different, that means there is something wrong with the prediction, which means the theory of gravity that you have used to predict these values do not produce consistent numbers for these different parameters. Now, within the degree of error, all of these measurements fall exactly at the same place when you use general relativity to predict them. So far, all measurements that have been carried out for tests of gravity are passed by GR in flying colors. But that is not to say that we are going to stop measuring departures from GR, and this is a process that is going to continue, and one will try to constrain the theory further and further and see whether GR is still the best theory of gravity or not. One of these measured parameters I said was the decay of orbital period, and here is a decay of orbital period graph. This is for the Hughes-Taylor binary pulsar. If there was no decay of the orbital period, the value would have been here, but these dots are the measured ones, and the solid line is the prediction from general theory of relativity. So you can see how well this matches, but this tells you the orbit is shrinking with time. So if you leave this orbit long enough, then the orbit will shrink and shrink and shrink and shrink, and there will be the two neutron stars are going to come very close to each other. And towards the end, these neutron stars will merge, and near that time, you would expect a very rapid change in orbital period and hence the orbital frequency. So this whole frequency change is going to look like this. And why is this shrinking? Is because gravitational waves is carrying away this energy. So that means if you try to find this object close to this point, then you are going to get the strongest amount of gravitational wave being emitted, and this is the amplitude of the gravitational waves as it approaches merger. So this waveform is a predicted waveform for two neutron stars coming close to each other and then eventually merging. Of course, here what is not taken into account is the neutron stars have a finite extent, and they can be distorted tidally. I'll come to that in a moment. But these are the 2 point objects coming closer to each other. This was thought attractive enough to invest in detectors for gravitational waves. This gave rise to the whole concept of LIGO. And of course, there was many decades from the time this was predicted and the LIGO coming online. But finally, in 2017, August 17th, we had a detection of the merger of 2 neutron stars. And this chirp waveform, this frequency as a function of time, and this is where the merger occurs, follows exactly the prediction as I showed before. But this was not the first merger that was detected. This is the first double neutron star merger detected. The very first merger that was detected by LIGO was 2 black holes. That is 150914. And this is the waveform, which with further analysis has now been further cleaned up. And you see the chirp waveform and merging over here, and then a ring down. A ring down is a characteristic signature of after merging, the black hole oscillates and then settles down while emitting gravitational waves. And there is a well-known predicted signature of how a black hole should ring down once you perturb it, and from general relativity, and this matches exactly that relativistic prediction. If you take this part, which is the decaying part, you not only have a fundamental, you also have an overtone, and the ratio of these two is exactly what is predicted by GR. So this is another test of gravity and another signature of strong gravity which you see. So in this case, there are 2 black holes of 35 solar mass and 30 solar mass merged to give a 62 solar mass black hole. 3 solar mass of material got converted into gravitational wave and left the system. Now, similar waveform can be observed for neutron star merger as well. And they will not be as clean as this, because as the 2 neutron stars come close to each other, they're tidally distorted. They become elongated, spaghetti-like objects, get disrupted and eventually merge. All of that signature is seen in the waveform. And those departures from point source or point mass signatures is a signature of tidal deformability of neutron stars. And how deformable a neutron star is depends on internal forces. It depends on the equation of state. So if you take the waveform of a double neutron star merger, you can reveal the signature of the tidal deformation and hence place constraints on neutron star equation of state. So it's another new constraint on neutron star equation of state from another relativistic measurement. And this has been done for 170817. So this gives you a compendium of all these systems which have been found by the gravitational wave detectors to merge and form objects. So basically you will have 2 points for the 2 components and then taking an arrow to the final component. So you have double neutron stars here. All the double neutron star candidates which we have resulted in black holes eventually. We haven't found a system yet where 2 neutron stars merged left a neutron star at the end. Maybe we will find this. And these are all the black holes that have been measured. The most massive ones, most massive product is around 200 solar mass. And these other dots are neutron stars which are not seen in gravitational waves, but they are neutron stars which are seen in electromagnetic wave bands. These are black holes which are seen in electromagnetic wave bands. This is a mass distribution diagram. So we have compact objects, a fair collection of compact objects which you can use for finding relativistic signatures and do this kind of studies that I'm talking about. Now finally, pulsars that we talked about can be used not just to probe strong relativistic phenomena near the surface, but because they are accurate clocks, they can be put to other uses as well. For example, if you have a gravitational wave of very low frequency, nanohertz, with wavelength of many light years coming to us, how are you ever going to measure it? So what does a gravitational wave do? Suppose you have the distribution of arrangement of masses like this. Once a gravitational wave passes, it is going to make these array of masses oscillate like this. So if you look at any two masses which are nearby each other, pick any two. If they are nearby each other, their motion is going to be correlated in the same direction. If they are sort of 90 degrees away from each other, the motion is going to be exactly antiphase. If one is coming closer, other is going to go further away, right? So from a collection of objects, if you now look at the correlation versus angular separation, you expect a relationship like this. And this is called Helling-Downs curve. Now what people are trying to do is to use pulsars as these test masses. If the pulsar comes close, the pulsar goes further away, pulsar time is going to reveal that motion. And you can then construct from a whole bunch of pulsars around us, you can construct this Helling-Downs curve and then see if you can find it. And people have been at it for more than 15 years. This is called pulsar timing arrays. Large part of the globe is involved, including India, where you have which is called INPTA, Indian Pulsar Timing Array. So, for example, GMRT is involved in that. So, all of that together forms the International Pulsar Timing Array, and they have been doing this for many years now. And a couple of years ago, the first detection results were published. This is from Nanograv, and there are also other results from EPTA and Indian Pulsar Timing Array. This is the Helling-Downs curve. So this is first detection of a possible Helling-Downs signature and a spectrum of the frequency of gravitational wave versus strength. So this is a stochastic gravitational wave background. Where is this being generated? Two top candidates are binary supermassive black holes at centers of galaxies, or primordial gravitational waves left from the very, very early phase of the universe, like inflation. But there are several other possibilities which are being explored. So I hope I have given you a flavor of various kind of strong gravity effects that we both see near compact star or use compact stars to explore. They are very good candidates for observing such signatures. And these observations are enabling measurement of various parameters of these systems, testing theories of gravity. GR so far passes all tests, and probing fundamental physics, including strong interaction at very small scale to the universe at the very largest scales. Thank you very much.